So thank you for the introduction, and thank you for having me here in the QFlux seminar, which I appreciate very much that we have it. I mean, it was very important in the time of the pandemics, but I think it's good that it continues. Although I didn't join so often live, I really appreciate also that we have the recordings of these meetings. Now, my talk today will about a very classical topic of quadratic form theory, which has to do with field invariance. But I will not talk so much on field invariance directly, but you will see from the flavor that it has to do with that topic. And I think the most important field invariant that we know about is the u-invariant. So it will not come up in the talk, but it is certainly behind the story that I want to tell you. So the u-invariant is the largest dimension of an anisotropic form over the given field. And yeah, so the way how you can determine whether the u-invariant is finite has been a topic of speculations and results that were crucial in the development of quadratic form theory. And yeah, one spectacular result in this was certainly the proof by Merkurjev in about 1986 that the u-invariant can be any even number, which he showed by a construction involving tensor products of quaternion algebras, and showing that you can have big tensor products of quaternion algebras while the cohomological dimension does not need to be large. And it has to do with this, what I want to talk about. Now, the term that I chose for the title, the Brauer 2 torsion index, I tell you what I meant by it, but it will not literally come up in the talk. So maybe the title wasn't chosen ideally. So I thought one could look at the largest degree that an exponent 2 central simple algebra over the given field can have. That's a natural thing to look at, closely related to another invariant, the 2 symbol length, which will come up in this talk. And so that's what it is, and you will possibly find it back, and if not, then the title was maybe not so well chosen. Okay, so as really in the old times, this quadratic form theory story starts by saying, let F be a field of characteristic different from 2. And now I have to get my environment working. Yeah, now it works. So let F be a field where 1 + 1 is different from 0. And you will soon see that this is a little bit more than just for commodity. One would really need to think the story anew if one wanted to make it work in characteristic 2. So quaternion algebras, I assume that people in the audience know what we mean by them. So we look at these algebras which we get from 2 elements of the field A and B, and which we then construct by starting with a 4-dimensional vector space F plus let me see, yeah, F plus Fi plus Fj plus Fk, and we put on these relations. I think that this is familiar, and this is the quaternion algebra, which we denote by this symbol A comma B, and we write an F to it. Yeah. So this is the one important base object that I need in this talk, and it has naturally a quadratic form associated to it, namely its norm form. So diagonal notation will be this here with these starting elements A and B. It will look like this: 1 minus A minus B AB as diagonal coefficients. And we have this abbreviated notation where we just, again, just denote this A and B. Now, there is a direct correspondence between the quadratic forms of this shape here and the quaternion algebras given by two elements. So both are given by two elements, and we can actually, even if we change the two elements, then the fact whether we really change the quadratic form or whether we really change the quaternion algebra is exactly the same. So we have the two norm forms are isometric if and only if the two quaternion algebras are isomorphic. And now, how does this go with tensor products? So we have a way of taking tensor products, in particular quadratic forms, coming up by this, the so-called Pfister forms, which is in an extended way what we already used for this norm form. Like we take tensor products of these binary forms representing 1 and minus a1 and so on. And that is the notation also that I will use for Pfister forms. So they arise by a tensor product construction. And then remember that these quadratic forms have special properties. So they are either anisotropic or hyperbolic. And I mention this because I will use it. And I will also say rather split than hyperbolic, simply for economy, because the word hyperbolic is so long for the page. Good. And now here the tensor products of quadratic forms, how are they related to the tensor products that we can take from quaternion algebras? That is basically the starting question. So suppose that you have now given not n elements, but in fact 2n plus 2 elements. And we look at the quaternion algebras that you can build up with the AI BI. And on the other hand, we look at the Pfister form that you can build with all these AIs and BIs. What is the relation between the two things, which are basically coming from a tensor product construction? Okay, so for example, if one of the, so what can we ask about the left side? Is it does this central simple algebra that we obtain by taking the tensor product of these quaternion algebras, does it have non-trivial zero divisors, or is it maybe splits? Or is it a division algebra? And here the quadratic form, is it split or is it anisotropic? And yeah, between these two things, we want to see whether there are relations. Now, Merkurjev's construction that he used to show that we can have a field with cohomological dimension 2 and any even u-invariant shows that we can have big non-trivial tensor products of quaternion algebras, while Pfister forms can be all split. So that is the one direction which already there is not too much relation expected. So you can never know from the, you cannot expect to know from the Pfister form too much about these quaternion algebras, because the Pfister forms, they might just all be the hyperbolic form, and nonetheless you have non-trivial tensor products of quaternion algebras. So this would follow, I would say that is quite related to Merkurjev's u-invariant construction. Now, on the other hand, can you maybe reason in the other direction? So could you say like, okay, but if this tensor product of quaternion algebras is very close to trivial or trivial, is then the Pfister form also split? Well, there is an easy counterexample to this if you ask it very naively, because look that I took a tensor product of n plus 1 quaternion algebras here. This is just for technical reasons. So just already the case n equals 1 is about the tensor product of 2 quaternion algebras. Now I could take all the AI BIs here minus 1, and I will get a split algebra, which I could as well get by taking just ones instead of minus ones. That would be over any field here. But over certain fields, I will have that this quadratic form, the Pfister form that I would get here for n equals 1, I would get a fourfold Pfister form, that this is non-trivial here, like 16-dimensional quadratic form with entries 1. And here you would get the hyperbolic form if you take the other coefficients that I took here on the right-hand side, the entries. So for the real numbers, for example, they would be different, although the tensor products are the same. So this sign problem is already in there, and you could now restrict to the case to get rid of the sign problem. Let's assume that -1 is a square, just to test. And this is in this case, actually, there is a relation. So in this case, and this is an observation which I learned from a paper of Bruno Kahn from 2000, I think, on comparison of some field invariants. It's called the article, that there is, when -1 is a square in the field, that the tensor product of these quaternion algebras somehow knows something about that Pfister form, although it's not the other way around. So let me describe this observation. So the thing that he says as some remark in this paper is that if every tensor product of n+1 F quaternion algebras is equivalent to a shorter tensor product, so this is really a complicated way of saying what is captured in the symbol length, but I don't use that for now. I will introduce it on the next page. So if you can shorten a tensor product of n+1 quaternion algebras to a tensor product of n quaternion algebras, then you can, well, if you can say the following, that every 2n+2-fold Pfister form will split after adjoining square root -1. And so in particular, if -1 is already a square, then every 2n+2-fold Pfister form over F is split. So if you have a bit of redundance in when you get to n+1 quaternion algebras in the tensor product, then you get split in the 2n+2-fold Pfister forms. Just the relation is like this. So go in twice as many, because the quaternion algebras bring already 2 entries with them. That's behind it. Now, the way how he shows this is by using divided power operations on the modulo 2 Milnor K ring. And that is an argument that really fascinated me. And then the problem of yeah, here you need -1 to be a square, that also fascinated me and occupied me for a while to think about it from time to time. Good. Let me first look at this relation a bit more closely. Suppose that just whether this 2n+2 is really good. It is good because if you take the field of iterated formal power series in 2n+1 variables, so just enough variables that you can build up the following 2n+1-fold Pfister form here, this will be anisotropic. That you will not be surprised about. And -1 is a square in this field. And on the other hand, this field satisfies the hypothesis. So indeed, over this field, every tensor product of n+1 quaternion algebras can be shortened. So it shows that I cannot possibly replace the 2 by a 1 here in order to get the same conclusion. So we are looking at the right degree for the Pfister forms. Now, in order to speak about some m-fold Pfister forms are split, I will now use just for notation, basically, the powers of the fundamental ideal in the Witt ring. You can really take this as a notation, and I even don't introduce it here as the power of the fundamental ideal, which it actually is, but just say the ideal of the Witt ring of F, which is generated by the classes of n-fold Pfister forms. It's the same thing, of course, and I just want to use in the sequel that I can write this ideal is 0, just as a shorthand notation for saying that every n-fold Pfister form over F is split. So I could say here every 2n plus 2-fold Pfister form is split. I could say I to the 2n plus 2 of F is 0. And let me reformulate it in these terms on the next page. And let me also reformulate the hypothesis where I said the n+1 quaternion algebras can be shortened. So I introduced this one invariant for today, the 2 symbol length. 2 is referring because the quaternion algebras live in the 2 torsion part of the Brauer group. So we take lambda f, called the symbol length, 2 symbol length, the smallest natural number n, such that a tensor product of n+1 quaternion algebras is always equivalent to a tensor product of n quaternion algebras. Here, like this, for all such elements from A0, B0 to AN, BN, we can also write them with A1 prime, B1 prime, up to NIN prime, BN prime, and write this tensor product like this. So I emphasized here that here it's n+1 factors, here it's n factors. So I shortened the representation. Good. And now let's look at the statement. Yeah, we should first also take the convention that we take infinity if such an n doesn't exist. And now we can reformulate or take a consequence of the statement of that I cited on the previous page. So suppose this lambda is finite, this 2 symbol length is finite, and -1 is and now this hypothesis is a bit different, is a sum of squares. So this is a consequence that actually Bruno Kahn gets. Then the I to the 2 lambda plus 3, the 2 lambda plus 3rd power of the fundamental ideal is 0. But notice also that we assumed a bit less than what was assumed on the last page. If -1 is actually a square, then it is really the I to the 2 lambda plus 2nd power, which vanishes. So this here corresponds here, this what is here in the last line corresponds exactly now in the new terms to the statement that I had on the last page. So if you know this lambda, such that we can shorten these tensor products of quaternion algebras, and -1 is a square, then the 2 lambda plus 2-fold Pfister forms are split. And yeah, and using this here, so this is what one shows first. One can, Kahn has an argument to see like how one gets this already when -1 is only a sum of squares. But you could still ask, since this here is weaker than the last conclusion, you could ask, like, can we not go from here to there? Can we not go downward diagonally here from this hypothesis to that? So this here is, of course, what characterizes what we call a real field, a non-real field, I'm sorry. So a field where -1 is a sum of squares, we call a non-real field. And do we have this relation between this 2 symbol length and the vanishing of powers of the fundamental ideal exactly in the same way already for non-real fields in general as we have it for fields where -1 is a square? So, well, I will tell you today that this is the case. And in any case, yeah, and good. So here's still the question that I'm giving the answer to. Is it enough that we have a real field, a non-real field to conclude that to get to the same conclusion? Okay. Now I will tell you about the method to tackle this question, and this has to do with trace forms of central simple algebras. So we take a central simple F algebra A, and let me recall to you what the trace form is. It's easy. I mean, we have the reduced trace. So which is really the trace in the case A is a matrix algebra. And if you enlarge the field and make A become a matrix algebra and then take the restriction to the original A from the trace, then you get a reduced trace. So this is a linear form on the vector space A. And now if before applying the reduced trace to the element, we square the element, we get actually a quadratic form. So, and the interesting thing is that this is also a non-degenerate quadratic form. And nonetheless, I must admit that for quite a while I knew that there are trace forms of several types of algebras, field extensions, central simple algebra. It didn't interest me that much. I thought like, would you really get interesting quadratic forms out of it? And was never so attracted by these trace forms as I got at least by this year when I made a computation that I want to show to you. So let's continue here. So so this here gives a quadratic form, and this is called the trace form of A. So by the trace form, I don't mean the linear form, I mean the quadratic form. Now, it has a nice property respective to the tensor product. The trace form of a tensor product of two central simple algebras is the tensor product for quadratic forms of the two trace forms. This is an observation which is easy to verify. You can, for example, you can reduce to the split case for let me not say anything about the proof now. So what you can use this rule for is also to look at the case when A is not a division algebra. When it has zero divisors, you get immediately that the trace form is isotropic. How do you get that? Well, if A is not a division algebra, then Wedderburn's theorem tells us that it is a matrix algebra over a division algebra with a non-trivial matrix algebra. So I can also write it as a division algebra tensor, a matrix, non-trivial matrix algebra over F. Yeah, good. So now then I basically reduced to showing that the trace form of a matrix algebra, different non-trivial matrix algebra over F, is isotropic, and that you can easily see. To find in the matrices over n by n matrices over F, a matrix whose square has trace 0, that is easy. So you will see in this way easily that a non-division algebra must have an isotropic trace form. So, but this is really a one-way implication. You cannot turn this around, but it will get useful. Let's now look back at quaternion algebras given by two elements A and B. Yeah, this is one of the reasons why I didn't like trace forms so far, because this trace form of this quaternion algebra doesn't look so nice as the norm form does. You have this quaternion algebra AB, and then you start computing, you get the trace form, you will get that it looks like this. So remember the norm form was 1 minus A minus B AB, and here you scale everything by 2 and switch on the pure part, you switch the signs. Good. Now, so far I didn't find this formula appealing, but somehow the twist that comes in, the two I'm still not so fond of that is in there, but the twist with the minus signs is really crucial in what I will do with this trace form and basically solving an essential problem. Good. Let's see that. So I want to still mention a couple of conventions that I will now use for two quadratic forms. I will write equality between them to say that they are isometric, and will write like 3 bars to say that they are width equivalent. So this here will be used for width equivalence. Now I want to still give a warning. There will a lot of 2's come up because of these 2's in the trace form of a quaternion algebra, and we should distinguish between making orthogonal sum of a quadratic form 2 to the n times or n times, and scaling the quadratic form by 2 to the n, which will really come up in the computations, both. And I take a different convention, at least than Lam's book. So I write really the scalars just in front. If the 2 to the n is just in front without anything in between this 2 power and the form, then it just means I scaled this by this non-zero element of my base field f. And it is a form of the same dimension. If I really want to take an orthogonal sum a couple of times, then I write this cross in between the number and the form. So just that you don't get confused on this. Good. Now we will do a computation with trace forms and quaternion algebras, and I will show you first what Kahn already had by this different argument on divided power operations. I will now use the trace form, and this idea somehow was given to me actually by Merkurjev in an email answer that he to some question in some very specific case, but he used the trace form, and I thought, hey, I can use this maybe more. Good. So recall that for the quaternion algebra Q, we had that the trace form looks like the norm form with the pure part twisted by the minus sign and everything scaled by 2. In other words, you could say this, we basically take minus the norm form up to with equivalence. It's minus 2 times the norm form. If I then add twice the entry 2, but instead of twice the entry 2, I can also add twice the entry 1, because that is exactly the same form. 1, 1 or 2, 2 will be the same quadratic form. So you have this basic relation between the trace and the norm form of the quaternion algebra. Here we have a 6-dimensional form, of course, and here we have a 4-dimensional form, but let's record this information like this. It will be used now. Now the statement is, again, if I have n plus 1 pairs of coefficients, and I assume that they form the tensor product of the quaternion algebras formed by them is not a division algebra, then and minus 1 is a square, then I claim that the quadratic form is split. So yeah, so as I said, this is already known and can be done by a divided power operation, but here now a different argument. We can just look at this, the quaternion algebras I will denote by Qi. The norm form of the Qi is this AIBI. So therefore the n2n plus twofold Pfister form that I'm talking about here in the conclusion is the tensor product of these norm forms of the quaternion algebras. But let's now look at this tensor product of the quaternion algebras, and let's look rather at the trace form. Since A is not a division algebra, we know that this trace form is isotropic. Now, on the other hand, we can, since minus 1 is a square, and if we look back now at this relation, we can already kill this minus sign here, it doesn't matter, but also this form here disappears. It's a hyperbolic plane, so could we really get T of TQ is 2NQ, 2 just scaled by 2, the norm form of Q. So the trace form and the norm form of the quaternion algebras are almost the same. And now we get that this tensor, this n2n plus twofold Pfister form is the tensor product of the norm forms. And this is up to scalar 2, the tensor product of the trace forms. So I took them out here. There are n plus 1 of them. So I took the n plus 1 exponent here out. But this is just a scalar. And this here is actually up to the scalar the trace form. But I said that this is isotropic because this is not a division algebra. So, but it's a Pfister form, therefore it must be hyperbolic. So this is a simple argument to see this relation. if the tensor product of quaternion algebras is not a division algebra, then this Pfister form is split. So since it's isotropic, it is split because it's a Pfister form. Okay, now I will want to do the same thing a bit more difficult. I want to not assume that -1 is a square. And what I assume instead is that one of the entries, I can say A0 here, is a sum of 2 squares. And I want to get to the same conclusion. Note that this will actually overrule this proposition, because if -1 is a square, then every entry, and in particular A0, will be a sum of 2 squares. So the next proposition, which I will also prove, will make actually this proof unnecessary, but this one is a bit easier to follow here. That's why I did it first, and also because I got to know this, I guess 6-7 years ago, and the other one I found this year, and I'm still. Yeah, good. Let me tell you the computation. So let's again have these 2n+2 entries. Let's build the tensor product of the quaternion algebras and assume that it has non-trivial zero divisors. And let's assume that A0 is a sum of 2 squares in F. And let's look at this form, this 2n+2-fold Pfister form rho. The claim is that it is split. Okay. Now, how do we show this? We will start by looking at, well, again, these quaternion algebras here, I abbreviate by QI. Their norm forms, I will even not abbreviate by NQI, but by NI. And remember that the norm form, the NI will be AIBI then. Now, the trace form, I will denote by TI. This stands for T of QI, the trace form of QI. So remember that we had, it is take the form 1, 1, and then add the orthogonally the negative of twice of the norm form scaled by 2. That was the rule that was formulated a page ago. And so this relation between the two things. Now, we also look at this tensor product of the quaternion algebras. That will be the algebra A again, as also in the last proof. But I also look at the tensor product where I drop the very first factor, where I start with 1. So I take the B to be the central simple algebra given by the tensor product of the QIs from 1 to n, and A, where I tensor that still with the Q0, with the very starting one. So this here is really, the A is what is here in the statement, and B is with 1 factor less. Good. Now, the factor that I singled out is the one where there is the slot A0 that was a sum of 2 squares. So I will calculate a bit by using this. So as A0 is a sum of 2 squares, if you look at what happens to this relation for 0, if we take I equal to 0 in this line. Now, so since actually, no, that is not exactly what we do. Let's see further. So what we have is that since the norm form N0 is A0, B0, this A0 is a sum of 2 squares. If I multiply, now really multiply in a sense or orthogonally, like I write this form twice, then since AI is a sum of 2 squares, this will get hyperbolic. This is like this. So if you have just, you just need to look at this one-fold Pfister form here. Since the A is a sum of 2 squares, doubling it will get a hyperbolic form. So we have this, and saying the same thing in a different way is also saying that N0 and minus N0, so N0 scaled by -1 is the same. They are isometric. -1 is a similarity factor of N0. So it's actually twice expressing the same thing, but we will use it in both ways now. Now I look at what N0 does in reaction, how does it react with these trace forms of the other quaternion algebras. So we have the T0, I can write without the minus sign. That's the only thing that really changes immediately. T0 is oh, this should be with equivalent, not equal, of course, here. So here we should add, and did not make any use yet of my pen. And I think I will just indicate it now because on the next screen it will anyway disappear again. So here this is with equivalence. And if I tensor now N0 with Ti, then you see that the Ti was 1, I should better look at this here, 1 orthogonal sum to -2ni, but up to with equivalence I could say, yeah, let's just tensor N0 with the right hand side here, but N0 multiplied with 1 will be hyperbolic because that is here. 2 times N0 is hyperbolic. So N0 times this part is uninteresting, and N0 times a minus sign, I can ignore the minus sign because I said minus N0 is N0. So N0 times Ti is actually with equivalent just to N0 times 2Ni. And since now the dimensions are both 16, it's really not only with equivalent, but isometry. So these I gave this nice relation. N0 Ti is actually N0 Ni scaled by 2. Good. And now that we can use. So, and now I will look at the trace form of A and the trace form first of B. The trace form of B I multiply with N0 just to see what happens. N0 tensored with this trace form of B. The trace form is multiplicative. So I can put the tensor product of the Ti's here from I to N, because B was the tensor product of the Qi's from 1 to N. I just replace it by this here using the multiplicativity of the trace form. So now I'm using for each of the factors on the right, how they react with the N0, that I can basically, I keep always the N0, but I can step by step replace the Ti's now by 2 Ni's. So I get this here because the 2 comes in each every time. So I get a scalar here, which is not that important. And I get the N0 and then all the other Ni's. So in total here, this here, which is almost our form rho. So this is the form rho scaled by 2n. So up to a scalar factor, which of course, I mean 2 to the n, up to a square, this is either 1 or 2. Yeah, so it's really a tiny detail. So good. Now I look at the trace form of A. Here I was calculating something, the norm form of Q0 with trace form of B, but let's look at the trace form of A, which is actually the trace of Q0 times the trace of B, because A was built up like this tensor product. Now, the trace T0 is 1 plus 2 norm 0, 2 n0. Good. So up to with equivalence, I can plug this in here. So I get 1 times TB, that is 2 times TB. So 2 times orthogonally seen this way. This is this bit times TB. And then I still have to multiply the 2n0 with TB. And 2n0 times TB, we calculated here up to the scalar factor 2, so which raises the exponent by 1, but we get this form here just from the previous side. So multiplying T0 with the 2n0 with the yeah, maybe I should have written one term more in the equalities. So I hope you can fiddle it together. So yeah, I'm using the relation for T0 here and combine it with this equality calculated here. And then we get this width equivalence between two things. The trace form of A is 2 times the trace form of B, and then plus a scaled version of rho, depending on the number of factors here. Now, this was the part where I used that A0 as the sum of two squares. I now do a second calculation where I use the other ingredient that we have, namely that this algebra has 0 divisors, that is not a division algebra. So since that is the case, we can actually, because it is of degree 2 power, we can split off, if that is not a division algebra, we can split off a 2 by 2 matrix algebra. So we can write it as M2F tensor B prime for a central simple algebra B prime. Note that both B prime and B are of degree 2 to the n. That will play a role in a minute. So I'm now computing once more the trace form using this decomposition. So I'm using the trace of the 2 by 2 matrix algebras. That was 2, 2, 2, minus 2, which is basically width equivalent to 2, 2, but 2, 2 is 2, 1, 1. So let's write it like this. So the trace form of M2, that is 1, 1. So that means that actually when I use the multiplicativity of the trace form again to calculate the trace form of A, I get the trace form of A is up to width equivalence 2 times, namely this binary form times the trace form of B prime. Good. And now we have it. We have to combine this information. We have computed the trace form of A in 2 different ways. We have 2 times TB prime. On the other hand, we have 2 times TB, and then orthogonal sum with a scaled version of rho. I want to bring this, so let's imagine it didn't fit in to make any more lines on the same page. So I'm sorry. So imagine to fit these 2 things together. And now you want to bring this term to the other side, just with a minus sign. So that's what I'm doing now. So I get basically that 2 copies of TB prime, and then orthogonal sum with 2 copies of minus TB will be equal to 2n plus 1, 2 to the n plus 1 times our rho. So rho scaled by that. And now, so this here is still up to a scalar. This is an n plus 1 fold Pfister form. It's a Pfister form. And here we have a difference. And now what I also now need is, recall that B had degree 2 to the n, dimension 2 to the 4 to the n, and this here had also dimension 4 to the n. So we have dimension 2 times 4 to the n, and then still times 2 will be dimension 4 to the n plus 1. And yeah, this here is unimportant for the dimension, but the dimension of rho is also 4 to the n plus 1. Yeah, so they have the same dimension, both sides. So they are not only width equivalent, they are really isometric. And here we have an isotropic form because we have 2 trace forms of the same dimension. This will always represent, is it 1 or 2? That depends then on the degree. Like 2 to the n, it will always represent 2 to the n. And this will also represent 2 to the n. They represent something in common. So this difference is isotropic. And therefore, the left-hand side is isotropic. And since these 2 things are in fact equal, which I stated already, we will get, since they both represent this number, we will get that this is isotropic. So we got that this form rho is isotropic, but it is a Pfister form, and therefore it is split. That's the whole thing. So I have a couple of minutes, I hope, to put this now to summarize the conclusions of this calculation made here. Now, in terms of the relation of how big can tensor products of quaternion algebras be, and how big can non-trivial Pfister forms be. So I will assume that basically this is in a hidden way is a field invariant that I'm talking about, but I could talk about lambda is less than or equal to m, the two symbol length, but this hypothesis is actually weaker. I'm not assuming that a tensor product of n+1 quaternion algebras is always equivalent to a tensor product of fewer quaternion algebras, but only that it has zero divisors. So we assume that there is no F division algebra of degree 2 to the n+1, which is totally decomposable in quaternion algebras, and want to get conclusions from this. So the first conclusion is that the 2n+2 power of the fundamental ideal of f square root -1 is trivial. Before I say something on how to get there, the consequence of that is this implies in particular that if you take the 2n+2 power of the fundamental ideal of f, that this is torsion free. There's some typical going down statement here that you get this torsion freeness. Now, if this is torsion free, this says in particular, if we have a non-real field, then it's zero. So if -1 is a sum of squares, then our assumption already implies, this follows directly from translating 2 for a non-real field, that this power is 0. So this is basically answering the question that I had a couple of pages before in the context of Kahn's observation. Okay, I will say something to these 3 dots, to 3 bullet points, but let me first state a fourth one here, namely that you can say even more. This is of course uninteresting if we have a non-real field, because item 3 already tells that this is 0. We don't need to know more. But if it's not a real field, then one can still ask, is there more to say about it than torsion free? In fact, what one can say is that the 2n+2 power of the fundamental ideal is divisible by 8, so by the quadratic form 1, 1, 1, 1, 1, 1, 1, 1. So it's multiples of this. Yeah, I will say something to it after here collecting the arguments for 1, 2, 3. So let me first say, if n is at least the symbol length as I defined it, then the hypothesis here is satisfied. But it might be a milder hypothesis, or it is generally a milder hypothesis, to assume that there is no decomposable division algebra of degree 2 to the n+1. Good. But it shows that this improves somehow. It makes a statement of Bruno Kahn in a way more precise. Then here, so for 1 to 3, what you need to use is what I call Ellman-Lahm theory. Namely, there's a paper, but I think this goes over a couple of papers from the 1970s. There are great work on quadratic forms and Pfister forms. So the property an you might know from Lahm's book also, and such stuff. So that is I call Ellman-Lahm theory, and that also says something. For example, how does the property that a certain power of the fundamental ideal vanish go down? And it shows, for example, the implication 1 implies 2, independent of any condition here, that this holds. And also, if you have, on the other hand, that this here is torsion free, what else do you need to know to have that this is 0? That's also treated by them. And what you basically need to show 1 is the following. You need to show about 2n plus 2-fold Pfister forms over f. First of all, that they split over f square root minus 1. And secondly, that they are already split when they have a slot that is a sum of two squares. So remember that these are exactly the two scenarios of my propositions where I showed that under certain conditions, the quadratic form must be split. And indeed, the condition to have this conclusion was that the tensor product of the n plus 1 quaternion algebras given by the AI BI, that this is not a division algebra, which is here assumed. So really, you get by the proposition, you get exactly what Ellman and Lahm would need as a condition to get 1, and that implies 2 and 3. So I would say I even proved more or less up to these old statements. I proved more or less completely to you why this 1, 2, 3 hold. I don't say too much on number 4. It is actually, well, I say something, yes. You show this in several steps. First of all, what you get easily is basically already captured in 1, that I 2n plus 2f is 2 times the previous power of the fundamental ideal. So it could write 2 cross I to the 2n plus 1f. And then you show in the next step that this is actually also equal to 4 times I to the 2n f. And then in another step that this is actually also equal to 8 times I to the 2n minus 1 f. And then you think now it's becoming too hard, we stop here. But no, in fact, it stops there. That is what I found somehow fascinating, that you can get this. And on the other hand, you can show you cannot get a 16 here. So I will end by giving you an example of a field where we would have this hypothesis. And tensor products of n plus 1 quaternion algebras will always have 0 divisors, but where you could not put here 16 and here 2n minus 2. So this is, I guess, a relatively easy example. Namely, you take the iterated power series over R this time in 2n minus 1 variables. And that gives you now, yeah, okay, from a TIs, you can just not make up 2n not make up n quaternion algebras, but n minus 1 you can get. And then since we are over R, we still have the Hamilton quaternion algebra. So we can make a big division quaternion tensor product of quaternion algebras that is a division algebra. But on the other hand, one can show that, well, maybe I show you the full ingredients here. So this here gives an F division algebra, this tensor product of n minus, no, exactly n quaternion algebras is a division algebra, but you will not find over this field any tensor product of n plus 1 quaternion algebras that is still a division algebra over this field. This is just not possible. I mean, yeah. And therefore, the hypothesis of the theorem is in fact satisfied for this field. But on the other hand, here, if you take the form that you get by taking the variables here, that is in I to the 2n minus 1, and you take it times 8, yeah, you can easily see that this is not equal to 16 times another form pi. So this will never be in the ideal 16th times I to the 2n minus 2. So you get that these two things are really, from here, they start to be different, even though this hypothesis on tensor products of quaternion algebras is satisfied. Okay, thank you very much for your attention, and I'm looking forward to your questions or remarks.
Thank you much. Thank you. Let's thank the speaker. So is any question? Any question?
What is known about the trace form of a general division algebra, say of degree 2 to the n. Not one of exponent 2 or decomposable.
Well, good. We can already sort basically by primary decomposition. We can take a prime power. Now, well, we should look at the split case because it's a quadratic form, and we can split now our odd degree algebra. We could split by an odd degree field extension, but the trace form will not basically change a lot by Springer's theorem. So yeah, so basically it will, I think it will not look more interesting than in the matrix case, what you get generally for a central simple algebra of odd degree. And then by primary decomposition, I would say like it basically reduces the interest to those of degree 2 power. Now, still there could be interesting trace forms maybe for algebras of exponent 4 or 8. So that's okay. That's just what comes to my mind. Maybe anybody who already thought for a longer time over trace forms than me can add something on it.
Thank you.
Okay. More questions?
Do you know if there's anything you can do characteristic free in this direction?
So including characteristic 2.
Yeah.
I think this is really interesting. I mean, at least in the way how I told the story, it's more than just putting things right. I mean, the whole role of the tensor product, we cannot talk about trace forms of quadratic forms and then say, oh yeah, it commutes with tensor product of the central simple algebras, because we cannot even take the tensor product of 2 quadratic forms, or at least not in an obvious way. So just to indicate that one has to rethink the problem.
Because for the special case of symbol length 1, it does generalize also to characteristic 2. So it would be nice.
Thank you for saying this. Please finish your sentence, but it brought me to something I still wanted to say. Yeah.
No, just you can say it, because I guess you want to say
okay,
more.
Yeah, you can. No, in fact, the whole theorem here is new, I guess, except for n equals to, now I should be careful since I start with 0. So for n equals to, n equals to 1 is, the assumption for n equals to 1 says exactly what the field is linked. So so if every tensor product of a Q0 and a Q1 is equivalent to a single Q1 prime, then we have a linked field. And these statements here, they correspond is quite exactly to what Ellman Lahm did in their second paper on the U-invariant, when they were studying the condition that fields are linked. And basically also this 8 times it then comes out by different ways in their computations, and is needed on their way of showing that the U-invariant of such a field can only be 1, 2, 4, or 8. So yes, that's. Did you want to add something, Adam?
No, just for. I guess it's true. Or it's certainly true for characteristic 2. That if you take a 4-fold Pfister form, then it has an Albert form as a subform. And that's the trick where you can show that if the field is linked, then the cohomological dimension is no greater than 3. But I don't know what kind of tricks you would need if you want a longer symbol length. It's an interesting direction.
Sounds good.
Okay, so more questions.
Yeah, I must. I saw Danny Crashen in the audience, and I want to say at least a word, since I'm addressed it in the abstract, but now didn't address it at all. That there a link to work that he did, where he also for some part of the work he needs to restrict to fields where -1 is a square. And okay, I mean, there I'm working on with his former student Saurabh Gosavi on extending this result to general fields. But the main interest, one should admit, is there. The main difficulty is there not to include general non-real fields, but to go also to address the real fields. That is basically made possible, among other, as a step also by this. Just maybe a cryptic remark, but just to say something on what I had mentioned in the abstract.